Alright, silly people, here's the situation. We're going to be looking at the odd parity solutions for the particle and the finite square well. Um, so Griffiths went through a solution for the wave function for the Schrodinger equation uh, for even wave functions, and he just said that it was like this, and it had a cosine here Lx, and then this is psi of minus x, and this is for 0 less than x less than a, and this is for x less than 0. Uh, this is for even wave functions, right? Because cosine is even, and then if you make it positive on the left side of the x equals 0, then yeah, this is all even. But we want an odd function, so what we can keep from Griffiths' solution for the Schrodinger equation, we can keep this term. That doesn't go away. Cosine isn't odd, but sine is, so we're going to switch out the cosine for a sine. So we have a characteristically odd solution. And then also, for this to be odd, it has to be minus what it is on the other side for x less than 0. Odd function. And so we can use boundary conditions to figure out what kappa is, or k, depending on how much you care. So first boundary condition we'll look at is that the wave function will be continuous at x equals a. So we have that psi of a plus equals psi of a minus, and so on this side this will be f e to the minus kappa a, and then on the right hand side we have d sine L A. Okay, and then we can just use this to solve for f. So it's going to be d e to the kappa a sine L A. And then we can use the other boundary condition. That is that the derivatives are actually continuous at the boundaries now as well. So we have del psi del x coming from the right side is equal to del psi del x coming from the left side. So this is looking like minus k f e to the minus k a over here, and then this is going to be L cosine L A over here with a D on it. Yeah, fantastic. At this point, we can plug in what we got for f, what we got with the first boundary condition. So it's minus k d sine LA equals dl cosine LA, and now you get that the d's cancel out, and you can solve this for kappa, which is going to be just kappa equals minus L cotangent LA, because it's cosine over sine. Now, I'm actually going to multiply both sides of the equation by a as well, to make what I'm going to do next seem like it makes more sense. I'm going to apply a bunch of coordinate transformations that Griffiths gives us. He defines a z as just being equal to LA, a z naught as equal to a over h bar times square root 2m v naught, and then it follows from all that junk that kappa a will be the square root of z naught squared minus z squared. Right. So we'll just plug those into our little expression here. So we have square root z naught squared, probably with a minus sign on this side, minus z squared equals z cotangent z. And let's solve this for cotangent actually. So we have that minus, and then in the square root, I'm just going to have z naught squared over z squared minus 1. We divided both sides by z. Equals cotangent z. And I'm going to show you the solution to this sort of equation in a second on Desmos. But I'm going to tell you right now that for large values of z naught, so for z naught greater than 1, that is for the case of the large, deep, wide square well, that the solutions to this are actually going to be Zn. There are multiple solutions, and each of them fall on n pi, so integers of pi, which means it's the same sort of solution for the even parity wave functions, but multiplied by 2. And so you can argue, just from a bit of symmetry, that you can add up the energy eigenvalues plus V naught will be of the same form as for the even wave functions that Griffiths provided. But before it was with odd n. This one is going to work for even n because we multiplied by 2. So this is for n is in the set 2, 4, 6, yada yada yada. So that's pretty epic. The next limiting case that Griffiths looks at is for the shallow narrow well. And so z naught is, we set it equal to a small value. And what I'm going to show you in a second is that if z naught is less than pi halves, then there is no solution to this equation here. Because, yeah, I'll show you in a second, it looks really weird. There's no solutions there. Which means that for a solution to occur, we have to have z naught greater than equal to pi halves for a solution. And that's actually going to set a lower bound on the potential value. So just using our definition of z naught from up here, we have that a over h bar root 2m v naught has to be greater than or equal to pi halves for there to be a solution. And we can quickly solve that for v naught. We have that v naught has to be greater than or equal to h bar squared pi squared over 8ma squared for solutions to happen. Now I'm actually going to show you the Desmos plot. Alright, so this is a Desmos screen. So I have here the left side of the equation that we had to solve for z, and here the right-hand side. Notice I just replaced z with z. Wait, no, I replaced z with x and z naught with z, so I hope it's not too confusing. But yeah, so in green is the cotangent function, and then purple is the function of z. And so if we set z to be really, really large, so 1, 0, 0, I'm just going to stop there at 100. It's pretty easy to see. We have solution here at what is pretty much 4 pi, and then there's 5 pi, and then that's 6 pi, 7 pi, and it goes on ad infinitum. I'm sure if I scroll down far enough, oh, yeah, there's pi. So yeah, it's being solved at integer values of pi. Um, so if we set z to be pi halves, we see that there's only one solution, and that's exactly at pi halves and 0. And if we go any less than that, so let's just divide by a little bit more, no solution now. There's nothing here. It kind of just, the lines never meet. And if you just make it smaller and smaller and smaller, that's not really doing anything. But there's no solutions once you go smaller. And so yeah, that's sort of the transcendental equation.